So the main point of this entire course, right? After all, the course is called an Introduction to Programming in C, right? And it is about the C programming language. So before we actually get into the C programming language, I would like to talk a little bit about the history of the language itself, right? Because understanding a little bit of that background will help in terms of appreciating why certain decisions or design choices have been made in the structure of the language, and that in turn will influence how you are able to use it and make use of the features that it gives you. So this is a picture from the 1970s. Well, not exactly, right? This computer existed in the 1970s, and this particular picture is something from, I've borrowed it from Wikipedia, right? It's an image of a PDP-7 mini computer that was there at Bell Labs, right? So there are a number of interesting things out there. Of course, number one over here is, of course, that this picture is not directly from the 1970s. I believe this is actually from an attempt at restoring such a system. But this is what a computer looked like in the 1970s. The first thing, there were no microcomputers, right? This was a mini computer, right? And you can imagine if a mini computer was this big, then what a regular computer looked like, right? It literally occupied probably the whole room, right? And PDP stands for Programmed Data Processor or Programmable Data Processor, depending on who you ask, right? And it was one of the sort of very interesting families of processors that were developed by Digital Equipment Corporation, right? So this came out in the 1970s, and Bell Labs, which is an offshoot of AT&T Research essentially, or rather that led AT&T Research at the time, they had a PDP-7, right? And Bell Labs is instrumental in a large part of the history of computer science. A lot of what we sort of take for granted today has some kind of origins at Bell Labs, or at least was influenced by some work that happened at Bell Labs, right? And as far as this particular course is concerned, these two people, right, their names are Ken Thompson and Dennis Ritchie, were essentially responsible for working on an operating system for this computer, right? And first of all, an operating system. What is an operating system? Many of you may be using Windows PCs, right? Some of you may be using Apple Mac, right? And hopefully some of you are using Linux based systems, right? Linux is probably the closest to the old Unix systems that exist, although the Apple Mac is also very close. And interestingly, for those of you who work with Windows systems, Windows now has what they call the subsystem for Linux, right? WSL, Windows Subsystem for Linux, all of which ultimately give you access to a Linux or Unix like system. The Apple, by the way, is not Linux. It is a different brand of Unix called BSD. But logically, all of them have their origins out here in the Unix operating system that was developed by these people, Thompson and Ritchie, right? And so what was the big deal about that operating system? Compared to the other operating systems of the time, it was actually a very simple and clean kind of design, right? And well, it has its own problems, but on the other hand, it tried to keep things as close as possible to the hardware, the computational power that you are actually dealing with, right? And just provide a way by which programmers would be able to build on top of that, okay? Now, what that actually meant was, when they started out, they were working with the PDP-7. All their previous experience with computing was on other machines, which had their own operating systems and their own languages, compilers, and so on. So in other words, languages already existed by that point, right? Fortran, right, which is available even today, which exists even today as a useful language, was available well before this. The problem with Fortran is it was sort of primarily geared towards a certain kind of mathematical computation, not so much at actually fiddling with the internal guts of what the computer can do. Not an ideal language for an operating system, in other words, right? So operating systems at that time were primarily written in assembly language, directly sort of coding into what the kind of sequence of steps that we looked at in the previous examples, right? So you have to break everything down into fine-grained steps. So when Ritchie and Thompson started work on the operating system, they found that the assembly language, yes, was possible, and in fact they didn't have a choice. They pretty much had to write something in assembly language, but it was highly desirable to have certain improvements upon it, right, which allowed you to effectively code at a higher level, so to say, right. So along with developing this Unix operating system, they wanted to have programs that were portable, right. And this word portability is something that you need to understand primarily because it's very important even today, right. Ultimately what it says is people come up with different kinds of processors with different features, right. Some of them may have hardware multiplication, some may not. Some may have hardware square root, some may not. Some may be able to do conditional branches in a single instruction, some may not, right. So there are many different kinds of processors that are available, and I don't really want to be I don't want to each and every programmer to have to understand the details of each and every processor that they want their program to run on, right. And effectively, especially when you are doing something like writing an operating system, right, every time a new processor comes out, it has a slightly different set of features, but the functionality is largely the same. I need to be able to access the various peripherals attached to the machine. I need to be able to provide controlled access to the different peripherals. That is the function of the operating system, right. So a lot of the logic over there is not specific to that particular processor. It is common across all kinds of computers, okay. So even though at the time most operating systems were programmed directly in assembly language, it was clear by this point, right, because the people had already been through multiple generations of computers, that you need some kind of a portable language that could target multiple different processors, right. And Fortran, for example, was not sufficiently good at this because its focus was somewhere else. It was primarily meant for formula translation, right. It was a math oriented language, right. So with all of that and the understanding that you have this process called compilation, right, which once again we'll talk about in more detail later. Compilation essentially says that it can potentially take a high level description in some language, right, and convert it into what is called machine code, which is the exact set of operations that runs on a given processor, okay. And with all of that in mind, what Ritchie and Thompson did was they started developing a new language. It was primarily led by Dennis Ritchie, right. So he is usually credited with being the inventor of the C programming language, but it was largely they sort of obviously would have had to interact closely with each other because Thompson was using it in order to develop many of the routines. Ritchie was responsible for sort of defining the language, the compiler, and so on, right. So they decided that yes, having a new language made sense. That new language should be something that allows you to get close to the heart of the processor, right, actually making use of the direct access to memory and so on, right, but abstracting out as much as possible so that it is easy, relatively easy, to switch it over to a new computer if you need to, right, a new processor. And one of the most interesting insights over there, which I'm only going to touch upon at this point, not get into details, is the fact that you had to have essentially something called the bootstrapped compiler, right. And this is a slightly tricky concept, right. What it basically says is, what you can always do is write assembly language, because that can be converted into the machine code of a processor relatively easily, because your assembly language is almost using the same instructions that the processor already knows. So using assembly language, I can write a program that will take C code, where C is some as yet undefined programming language which is written in a slightly different format, and have that converted into assembly, which in turn will go to machine code and will run on the processor, okay. So that effectively is your first stage compiler, so to say, right, which basically takes your C code and converts it into assembly and machine language. But here's the interesting thing. What if the very first program that you write in, that you compile in this way, is something that in turn can take other C programs and convert them into assembly language, right? At that point, effectively what you have said is, you needed one small core requirement that could take some part, one particular program in C and convert it into assembly. But once you have done that, everything else basically is just written in C and compiled using the C compiler. You actually don't need to touch assembly language again. Okay, this can potentially be a little confusing because we haven't talked about compilation yet. If so, don't worry about it. It's just that it's an important insight and good to know, right? And good to revisit when you understand more about compilers later. Now, this background sort of explains why C is so popular, right? It was designed specifically so that it could be very close to the hardware and the operating system, right? And it also had minimal requirements, meaning that there was a very small amount of work that was needed in order to retarget this or get this working on a different processor, right? What that in turn has meant over the next nearly 50 years at this point, or more than 50 years at this point, right, is that C has emerged as a very good target for any new processor or system, right? What that means is that you have a core requirement. After all, when I come up with a new processor, the only thing that is well defined for it is its machine code, and close to that is what we call its assembly language, right? And what C is saying is, as long as you can take a little bit of that and write that initial part, that C compiler, you can then bootstrap everything else. You have a C compiler at that point, and everything else that has already been written in C can then be compiled for this processor that you have created fresh. Okay. This means that it usually ends up being the most common first language other than assembly language for any new processor, right? So from the point of view of the computer, it's probably the simplest and easiest language to implement, right? And from there you can then start compiling various other things and get them running on the same processor, right? It has stood the test of time, as you can imagine. For the past 50 years, it has consistently been pretty much the first target that people look at. Now, there are certain properties that people talk about when they talk about the C programming language, right? Once again, there's a little bit of jargon out here. I'm just going to put it out here. You don't need to worry too much about this. You don't need to, I mean, it's good to sort of know these terms, but they will become sort of clearer as you work with the language more. The first thing is, it's an imperative language. Now, what does imperative mean? It literally means to give commands, right? And what this is saying is that we are able to write the instructions, the machine instructions, the sequence of steps to be followed directly as a set of commands to be sent to the processor, right? When you look at it from the point of view of the CPU, that makes perfect sense. That's exactly what the processor is looking for. But when you think in terms of how do I solve a problem, right, an imperative style of programming is not always the best, right? And in fact, there are a number of other programming paradigms, so to say, right, which have better properties in certain contexts, right? The beauty of the imperative programming style, of course, is it's the one closest to the heart of the processor, and therefore it's probably the easiest to get it working, right? It's in the tradition of a whole family of languages, right, which have their origin with this language called ALGOL, which is basically algorithmic language, right, from the late 60s, early 70s, that kind of time frame. And ALGOL influenced many other languages, but by itself was like too complicated to really take over as the main language that others use. There are data types associated with different parts or different kinds of variables, as we will see, right? When we get to how you declare variables and so on in C, we will find that there is a concept of data types, and C uses what is called a static type system. Those of you who have done other programming, maybe with Python or with JavaScript, those are both what are called dynamically typed languages, right? I mean, you do not specify that something is an int or a character or a string ahead of time. You don't need to, right? And it will sort of infer it based on what it sees you doing with the value, right? But C can't get by with that. It actually requires you to declare everything and say, okay, this is an integer, this is a floating point number, this is a character, and so on. Having said that, it is also what's called a weakly typed system, right, where converting from one type of value to another is actually quite easy, right? And there are languages where this is not permitted. So for example, if I want to convert from an integer to a floating point number, I actually have to be very clear and explicit to the language that yes, I want to perform this conversion, right? In C, a lot of that sort of happens quietly behind the scenes, right? It's good in some ways because it makes certain kinds of programming easier. It is also very bad in certain other ways because it makes certain kinds of bugs easier to enter the system, right? Now, from the point of view of the programmer, it supports what is called structured programming, right? Once again, structured programming is a very simple concept. All that it's saying is rather than having one long sequence of instructions, you can break it down into smaller blocks, each of which solves one particular problem, and combine those blocks together in order to solve the overall problem that you are dealing with, right? Once again, we will be using a lot of this when we get to functions and the scoped, the block scoping that is used in order to structure programs more cleanly, right? And of course, one of the interesting things which is not by itself a major property, but it happened to be something that made it very convenient for people to write C code, was the fact that a C program is just pretty much free form text. It's just a simple character set, right? The English alphabet, numbers, a few extra symbols, that's about it. Just put them together and you have some kind of syntax which says what characters are allowed to follow what and how they are grouped together and so on. But overall, there aren't too many rules. It's relatively easy to just take a text file and parse it, interpret it as a language, right? Now, even a language like Fortran actually had slightly more rigorous restrictions. For example, comments had to start at a particular line or a particular column number. If you look at something like Python, it has the white space restrictions, right? I mean, all your indentation is important. That by itself is not a problem. That was introduced for a reason, to improve readability. But at the time in the 70s when C was introduced, the fact that it was just simple free form text only added to its ease of use, so to say. Okay. So now let's get to the important part over here. How do you go about learning C, right? And the first step for that would be you write programs. The second step would be write more programs. Third step would be write still more programs, and so on, right? And this is pretty much true of any programming language, right? You are not going to learn a language by learning its syntax, right? So that should be very clear to you. You can never learn a language just by viewing a set of video lectures. You have to work through the assignments. You have to actually write code. And you have to make mistakes. You have to learn how to debug them. That's pretty much the only way that you are ever going to learn how to program in any language, right? So what we are trying over here is, of course, to give you as much background as possible so that the concepts fit in. But the only way you put that into practice is by actually writing code. Okay. And finally, a little word about reference material, right? As you can imagine, this is a course that is trying to teach you a programming language, and as I mentioned just now, the only way to do that is by actually writing programs, right? What I have put down over here are things that I have found to be sort of useful reference material, right? I am intentionally not using the word textbooks because it doesn't really make sense to talk about a textbook for a programming language, right? It is not something where you learn chapter by chapter and you go through. You need to understand all the concepts in order to use the language effectively, right? And it's not like it necessarily follows a sequence. Now, having said that, the most sort of, in some sense, the most fundamental book related to C programming is called the C programming language, and it's written by, again, two people from Bell Labs, right? One of them is Ritchie, of course, who is the inventor of the language, so to say, and the other person is Brian Kernighan, right? So Kernighan and Ritchie wrote the first book sort of bringing out the details of the C programming language. Even now, it is an extremely useful reference, and it's a very simple, relatively small book, relatively thin book, right? Given the kind of things that you would normally find in order to try to teach a language, right? Apart from this, of course, there is also something called the C language reference, right, which actually gives you the full rules of the language. That's much harder to read, so I would not really put that as a reference material, although at some level, if you are interested in the language, you probably may want to go and look at that. In general, the C language reference manual is more useful for a compiler writer, someone who's actually trying to create a compiler for C, not so much for someone who wants to use the language, right? For people who want to use the language, this is a very good starting point, right? It's usually referred to as the KNR book, right? Konigan and Ritchie. Apart from that, there is a book from O'Reilly Publishers by Steve Uelin called Practical C Programming. I believe now it's in the 3rd edition. Having said that, the 3rd edition is from 1997 or so, right? It's a relatively old book, but once again, the language is much older than that, right? So it's not that things have that it's obsolete. Please do keep in mind that the language has been evolving, right? A lot of things have been added over the years as extensions and modifications to the language. And wherever something is going to work only on one particular version of a compiler, I'll try and make that clear, right? And as far as possible, we are going to be interested in using the latest and greatest features if possible, right? But at the same time, the primary intention of this course is also to keep things relatively simple, right? We want to understand concepts rather than going too much into the details of how a language can be used in certain ways, right? And finally, there is also this online reference I've come across called Beach's Guide to C Programming, right? And I've just put the link out here, you can search for it, which also has a fairly, a very structured and systematic, run through of everything in the language itself. Needless to say, this is an old language, it's been around for a long time. There are innumerable online sources that you will encounter at various points, right? The only thing I can say about them is use them with care, right? Verify what is written in those sources. The best way of verifying is usually to write your own programs, right, and understand them, right? Because there may be some that talk about certain styles of programming, there may be some that talk about certain kinds of behavior that can be expected, there may be some that start talking about how to optimize or get better functionality, right? Do not try optimizing something until you understand why it is slow in the first place, right? That's one general piece of advice that I can think of. But apart from that, anything else that you see in terms of, this is how it should be done, this is the only way to do it, use your judgment, right? And try and understand how things, what impact any of those choices is actually going to have on the programs that you write. So, like I said, this is some reference material, it's not exactly a set of textbooks, but these are good sort of, fallback material that you can get, go to if and when you have questions about how the language should be used.